One really neat application of circular motion, Sean, is artificial gravity. One method to create artificial gravity in outer space would be to build a circular space station and then spin it. Something like this. You may have seen it done in movies before as well. So let's look at the physics of how that might create an artificial space station. So here's a space station of radius 35 meters. What does the period need to be if we want the astronaut to experience 80% of Earth's gravity? Follow the argument? Okay. What path is this person tracing out? You know what this is a good job for? Free body diagram. I'm going to do the free body diagram right on this top view, I think. What are the forces acting on this astronaut? Get the up. Sorry. Are we in outer space? Let's assume there's no gravity. We're far enough away that gravity is negligible. Okay. What path is this person tracing out? A circle. Where must the net force be pointing? Toward the... So I know, even though I'm not sure what it is, there has to be a force that way. Now, that's going to be FC, but FC isn't what shows up on my free body diagram. I need to figure out, hey, what force is that? So it's not gravity. Any thoughts on what force that is? What? Is it the surface, the ground pushing up through his feet or her feet? You are correct. It's the normal force. And this is why we also call the normal force your apparent weight, because out in 0G in outer space, we can still give you a fake weight, an apparent weight, if we can create a normal force for you. There's my free body diagram. Who's winning? It's meant to be really obvious. Normal force. Who's losing? So I'm going to get this. Normal force equals FC. Now, Colby, this question told me how big we want the normal force to be. How big do we want the normal force to be? 0.8 mg. 80% of Earth's gravity. That's going to equal m. And then normally I'd write AC. However, Maddie, does this question want me to find the period or the speed? And how do we know? Oh, so I'm going to use the 4 pi squared r over t squared. Johnny, do we have to have astronauts step on a scale before we send them into outer space? Look at the equations. Oh, come on, people. You were the one I went with last time. I told you this was going to be your cue. Yes?
Yes.
What do you notice in this equation? M's cancel. By the way, we still do have to have them step on a scale because we have to plan everything accurately. Every kilogram costs money, so it is true. But once we built big space stations, could little kids and grown-ups live on it successfully? At least in terms of mass, yes. And I'm going to tell you some problems with this in just a second. But for now, what's this question want me to find? How would I get the t by itself? First thing I would do is I would multiply the t squared over because I don't like it on the bottom. I would take the 0.8 g, move it down. Yes? So I would have this. T squared equals 4 pi squared r over 0.8 g. What would my final step here be? Square root. So it's going to be 4 pi squared. What's the radius? 35 meters. 0.8 times 9.8. How many seconds should it take for this space station to rotate? Because that's what the period is. What do you get? I get 13.3 seconds. 13.275, 13.3. Anybody else? Yeah. Now, if we did that, then you would feel as though there was 80% of gravity acting on you. There's some problems with this, though. That's what you would feel on your feet, 80%. What's the radius of this spaceship? 35 meters, which isn't that big. You would feel a different force of gravity on your head. If we recrunch this, let's say you had a height of 2 meters. If we quickly recrunch this for 32 meters and actually found what you felt over on this side, you would notice a difference. You would probably feel like you were always just about to fall backwards. It would be uncomfortable, because you could tell that your feet physiologically were feeling slightly a different force and rotating slightly faster than your head was. And you'd either get used to it or you'd probably feel car sick all the time, air sick all the time, space sick all the time. So this works well, but you got to have a fairly big radius, Victor, so that your body's radius, your body's height becomes negligible and there's not much of a difference in G between your head and your feet. But otherwise, sure. What's the frequency of rotation? What did I find in part A? Period. What's the frequency? How do I find frequency if I know period? Frequency is 1 over the period, or the reciprocal. You know what? All of you on your calculator actually have a reciprocal button. It's that little x to the negative 1 button right there. Oh, hang on. Don't hit square root, Mr. Dueck. Come on, Mr. Dueck. Hit the right button after all that. Frequency would be 0.0753 hertz. You'd probably, if you were an engineer, say it's about 75.3 millihertz, because we tend to use the metric prefixes with hertz. Okay. Rotates every 13.3 seconds. It has a frequency of that. That means it rotates 0.0753 cycles every second. That's how far it gets around in 1 second. 1/13th, roughly, of the radius of the total trip. Suppose the astronaut begins to climb a ladder. Maybe there's a ladder that runs along the spoke of the circular space station. At what radius will the astronaut feel 30% of their weight? What's this question asking me to find? Okay, it's going to be the same question or the same approach as before. It's still going to be normal force is what's pushing me in a circle. How big do we want the normal force to be this time? 30% of mg equals m. And I think I'm going to use 4 pi squared r over t squared. Why? Well, I know the period from part A, and V would change depending on the radius. I'd have to calculate V, because as I move further and further up the ladder, my tangent to the radius centripetal speed is slower and slower and slower. Johnny, would a heavy astronaut and a light astronaut both feel 30% of their weight? Why? Hey, you're with me now? Here we're trying to get the r by itself, so I guess it's going to be 0.3 gt squared divided by 4 pi squared. Did I do that correct, folks? By the way, this unit and the next unit, Victor, on rocket science and orbits, this is what I always had in mind when last year I started preaching formula manipulation at you. Because to try and do these otherwise with numbers, it's a pain. But to be able to rewrite these is glorious. So it's going to end up being 0.3 times 9.8 times I'll use 13.3. We'll be off by a tiny bit, but that's okay. Don't forget the squared, Mr. Dueck. All over 4 pi squared. What was the radius of the space station originally? So there's a bit of a built-in error check. I better not get an answer bigger than 35, because that would mean somehow I'd gone outside the station and was spacewalking. Yes? 0.3. Again, I mentioned to you, all of you want to follow on your calculator because we're going to be doing some very complicated work, especially next unit. This is starting the practice. Times 9.8 times 13.3 squared divided by bracket 4 pi squared. Do you get 13.2? Yep. So a little more than halfway up. Half of 35 would be 17.5, so a little further than halfway up, and you're feeling 30% of your normal, your apparent weight. What would the force of gravity be at the center of the space station? What? Yeah, and so if we did build massive city-sized space stations, we would have a tube, an axis along the center where there was no gravity. You might turn that into a sports zone, or you might have an area where there was maybe 1% of gravity, and that 1% might be enough that you could actually strap on wings and fly there like a bird. You could practice flying, or you could do some really interesting stuff if we ever do go that industrial. What if you put a swimming pool there? Maybe where there's 3% gravity, so it's lining the very edge of the spinning axis, but you could do some really interesting stuff if we do ever get that far and get that technology. 0 newtons. Cool. Sci-fi writers have had fun with imagining all sorts of things, and you've sometimes even seen it in movies. What could you do with a 0G environment? A great playland ride. Oh, I like example 2. I like example 2. I like example 2. Example. Is it an amusement park ride? Yes, so I like it. A great ride at Playland is called the Gravitron. It's the one that spins around really fast. And then there's 2 versions. In some versions, the floor drops away. And in some versions, the ride tilts this way and you're leaning back against the wall. I almost said you're getting pressed back against the wall. You're not. You're getting pressed forward from the wall because the force is towards the center. How many of you have been on the Gravitron before? A couple of you? Until last year, Maddie, I'd never been on it. It's at Playland, but it's part of the Peonies ride package. And because I go to Playland every year with you folks, I usually don't go to the Peony. I'm too cheap to pay for the rides twice because I've already gone once. But last year, they had a couple of Playland's main rides broken. The roller coaster was broken. And so they brought in the Gravitron, and I finally got to go on it. Yes, great. So here's a side view. It spins its riders around in a circle. In this one, rather than having the ride tilt up, we'll have the floor drop away so we can keep everything horizontal. The ride has a radius of 4.8 meters. It rotates every 2.5 seconds. What's the minimum coefficient of friction required between the riders and the wall of the ride? Is there a coefficient of friction required? You know what this is a good job for? Okay, free body diagram. What are the forces acting on this rider? Get the obvious one. Is this rider sliding down the wall? Is this rider sliding up the wall? Then forces must be, I'm looking for a word that begins letter B. So I know there's a force up the same size as gravity. I gotta be honest, I'm not quite sure which one that is. I'm gonna hold off. I know it's there. Oh, what path is this person tracing out? So where must the net force be pointing? Toward the... So there has to be a force this way. It's not FC. It'll be FC in my equation, but not on my free body diagram. What force is that? What? Oh, it's the surface, it's the wall, it's the normal force. Now, as soon as I do that, does that help you guess what this vertical upwards pointing force might be? It's friction. Oh. So the gravitron wouldn't work if you were leaning back on ice. Or you'd have to spin it really fast, because I guess ice has a tiny bit of friction in real life. If you were leaning back on perfect ice, though, it wouldn't work. All right. Who's winning? Normal force is what's pushing me in a circle. Maddie, am I going to use the one with the V in it, or am I going to use the one with the T in it? And that's, at Playland, going to be usually the easiest one to get. So you would just watch the ride and time how long it takes to go around once. So it's going to be M4 pi squared R over T squared. What about the left-hand side of this equation? Well, here's what I usually say. I don't know the normal force. Oh, but look. Oh, no, I can't say, oh, but look. I know another force the same size as the normal force. So I'm just going to drop the Fn down and pause. Any suggestions now? There's another equation hiding in this free body diagram. You see it? Think vertical. Michael, can you write me a vertical force equation? Say that again, what? The second equation hidden in here is that. How does that help? Friction is what times what? Mu times what? Mu times what? Ooh. So you're telling me I can also say mu times the normal force equals mg? Which would mean if I go da-da-da-da-da, zoom. Here, this is a bit different. Normally I've said, I don't know the normal force. Oh, but look. Here, what I had to say is, I don't know the normal force, but fortunately, in a completely different set of equations, a normal force does appear. I can replace the normal force with mg over mu equals m4 pi squared r over t squared. Johnny, can little kids and grown-ups go on this ride? Yeah, why? Oh, really? That's kind of nice. What's this question asking me to find? Now, pause here. I like this question. I would have no problem giving you mu and asking you to figure out the period, or giving you mu and the period and asking you to calculate the radius of the ride if you were the ride designer and you knew what kind of an engine you had and how long it would take to go around once. In other words, to me, there are 1, 2, 3 variables in this setup, and as far as I'm concerned, I can give you any 2, you can calculate the third, and you can do the engineering. Is that all right? Here, we're trying to get the mu. Where is the mu right now, Victor? On the... Yeah. Oh, let's multiply it to the top, move this to the bottom, and this t squared to the top. Right? I think I can go like this. GT squared over 4 pi squared r. I think that equals mu. So it's going to be 9.8. What was the period? 2.5 seconds. Don't forget the squared. All over 4 pi squared, and r was 4.8. Hey, what's mu? I don't know. What's mu with you? 9.8 times 2.5 squared divided by 4 pi squared times 4.8. You get 0.323. That seems about okay. Now that's minimum mu. Probably there's way more than that to build in a good safety margin, because here you would probably feel like you were about to slide down. You would be right on the threshold of, I don't feel safe. And I've been on this ride. You do feel like you're getting pressed back because it's going fast enough that your inertia is such that it needs a fairly big force to push you towards the center. What I would love to do on the Gravitron, if I could, is I would love to go on there with a big bunch of ping pong balls and have a student across from me and see if, while it was moving, we could play catch. I think that would be fun to try, because we would see the Coriolis effect. They would never let me do that. Samira, what's B want me to find? Centripetal speed, that's VC. That is on your equation sheet. It was distance over time. Oh, it was the circumference. It was 2 pi r over the period. It's going to be 2 pi 4.8 over 2.5. How fast are we traveling sideways, tangent to the radius? 2 pi times 4.8 divided by 2.5, 12.1 meters per second. What else could I ask? Oh, by the way, instead of giving you the period, I could give you the frequency of the ride in hertz, and that's giving you the period. Here, I gave you the period. The frequency is 1 over the period. Victor, that means the period is also 1 over the frequency. So it's going to be 1 over 2.5. 1 divided by 2.5. This ride goes at 0.4 hertz. I could have given you that instead of the period. Show Gravitron picture. Where's my Gravitron picture? Here it is. Right? So you got the one person standing up like that. And apparently someone nearby clapping or applauding, saying, I'm impressed, you were able to stand. No, good physics. Example 3. The picture below shows a frictionless tabletop in top view. The mass is 4.5 kilograms, and it's attached to a long string and moving at 2.5 meters per second. Write force equations and solve for the string tension. Okay. James, what's this question want me to find? I'll give you a hint. Solve for the, it's in front of you. What does it want me to find? What does it want me to find? Say it again. Like you were feeling right then because you were zoning out. You're back now, yes? Okay. You know what it's a good job for, folks? What are the forces acting on this? Now, the first two I'm not going to label. Gravity is acting straight into the page, like it's going straight down. I'm not going to bother putting that on my diagram. And normal force is pushing straight up out of the page at me. I'm not going to bother putting that in my diagram. What path is this object tracing out? So I know there has to be a force pushing towards the center. What force is that, James? Yes. And so what's my equation? Tension is what's pushing me in a circle. Tension equals M. James, am I going to use the one with the V in it or the one with the period in it? They gave me the period in this question. Read carefully, please. Why? Because they told you it was moving at, okay, you with me now? So I'm going to use the mv squared over r. Otherwise, it's a straight plug and chug. Tension is going to be m, 4.15. V squared all over r. Mateo, what if I went twice as fast? What would happen to the tension? Would it be twice as big, 4 times as big, half as big, or 1/4 as big? 4 times larger? Good, I knew you'd get the hang of that. Let it go, Mr. Dueck. You get 13.0? So there's a neat version of this if you turn the page. And I think I like this question. I think I like this question. I think I like this question. It's my way of saying I haven't looked at my test recently, but I think it shows up. It says this. We have a small ball, and it's attached to a large mass. Okay? This mass is much larger. It's 10 times bigger if you look at the scientific notation. So normally, this mass would go straight down, and it would pull this small ball right into there, kathunk. But what we're going to do is we're going to get this spinning. And when that happens, let me pause the video for a second. This, hit myself in the head. We're all good. Dylan, what's this question want me to find? Speed. Wow, that took away. Yeah, okay, you with me now? You know what this is a good job for? I'm going to do a free body diagram. I'll use big M, capital M for the bottom mass. I'll use lowercase m for the upper mass. Let's do the bottom mass first. What are the forces acting on this bottom mass? Get the obvious one. Big M, G. What else? Tension. Does FC or anything go on this bottom mass? Is this bottom mass moving in a circle? No. Okay. This little mass here, I'm going to have little mg, normal force. What path is this little mass tracing out? A circle. So which way is the net force pointing? Toward the... So I know there is a force pointing that way. Which force is that? Oh, also tension. Okay. So, Dylan, what does this question want me to find? Well, tension is what's pulling the small ball in a circle. What's this question asking me to find? Tension equals little mv squared over r. I guess V is going to be tension times R divided by M square root. Do I know R the radius? Yeah. Do I know little m? Yeah. Do I know tension? Hey, there's another equation hidden in here, a vertical one. Here, is this thing moving up and down at all? No. So that must mean this is an equilibrium. I can say big mg equals tension. And I can stick that in over here. So I'm going to get this. The speed, that magic speed that you saw me doing, which was keeping everything in equilibrium, it's going to be the square root of the big mass times little g times the radius divided by the little mass. The m's, Johnny, this time don't cancel. They very much don't. Well, I don't need quite such a big square root. And so it's going to be the square root of 3 point, you know what? .036, that's easier to write. 9.8. What was the radius? 0.42 divided by 0.009. This might work out nicely. I think you're going to get a nice square root. This is a chance. Oh, I stand corrected. I thought you might. Do you get 4.06? Yeah. Meters per second. If I spin it faster, that bottom mass will start to get lifted up. If I spin it slower, that bottom mass will start to sink down. Also, we're assuming that little hole is frictionless as well. The example that I gave you, that little model here, there's actually a lot of friction between the string and the hole, which is why it wasn't quite as noticeable. But you got the idea, yeah? I definitely like example 5. Example 5 is a nice question. Now we're going to go at an angle. Most road corners are not flat. Most road corners are banked. Certainly highway on-ramps and off-ramps are banked because you're going quite fast. Racetrack corners are banked, usually. So an engineer is designing a curved exit ramp coming off of a new freeway. She decides to make the corner a banked corner at an angle theta as shown below. She wants to remove friction from the equation so that the corner will be safe regardless of the driving conditions, whether it's rainy or snowy or a nice sunny day. If the corner has a radius of 55 meters and theta equals 23 degrees, what speed limit should be posted for drivers approaching this corner? I already hope I told you I like this question. I like this question. This is probably almost certainly going to be one of your written questions because it's such a neat idea. Okay. Assume that this wheel is actually touching. I couldn't quite get it to touch, and so, okay. Any thoughts? How might I start? Free body diagram. William, what are the forces acting on this car? Get the obvious one. Sorry? I agree. What else? Nope. Patience. What else? By the way, William said, is there going to be an inwards force? There is. We're going to take a big jump here, so patience. No. Even before that. Is it sinking into the ramp like quicksand? Is it flying off the ramp like Superman? There's a normal force. Okay? Those are the only two forces acting on this. That's all you need. We're going to ignore friction because we're going to design this so that friction is irrelevant. Okay? And here's where I have taught you bad habits. Well, I've taught you good habits. See, here's what William was trying to do. William was saying, I see an angle. Did I say angle? This is a job for not components this time. And the reason I don't want to go components this time is I want the circle to be horizontal. Okay? That's the circle. That's not a force. Don't put that on there. But the circle that we're tracing out is a horizontal circle. Looks like it's about 5 meters off the ground or a few meters off the ground. But that's the circle that we're tracing out. Those are the only two forces acting on it, and they're vectors. What I'm going to do is I'm going to add them together. You know how I'm going to add them together? Draw them. Draw them. Tip to tail. And William, here's the key. I know what the resultant is going to look like because when I combine these two forces, the net force is pointing toward the... Okay, you ready? So over here, let's draw. I always draw the easiest force first. There's gravity. Then I'm going to draw the normal force. Why would drawing it like that be way too long? And why would drawing it like this be way too short? Tell me when to stop. Ah, there is the normal force, and that tells me that FC is the vector sum, the net force, the combination of only those two forces, and it's pointing towards the center. See it? Is that okay? Give me 1 second here. Pause the video. So far, so good. It's called attention span. Nina, you back here? Okay. Color. Well, that's definitely 90 degrees. It kind of looks like it goes down there. Let's see if I can do a proof. Well, here's what I notice. If that's 90, that's theta. You know what? Yeah, there's theta. Right? That looks like the same triangle tilted. FC, opposite, adjacent, or hypotenuse. MG. Now, Fn is hypotenuse, but I don't know the normal force, and there isn't any easy, oh, but look, and I probably could, but for now, I know Mg, and it's nice and vertical, and I know opposite is what I want to find, so I'm purely going to use those two. Which trig function? Tan. I get this. Tan theta equals opposite over adjacent. By the way, William, what's this question asking me to find? The speed limit. I don't see a... Oh, we're going to use the v squared over r. Let's get the FC by itself. FC is mg tan theta. Is that okay? mv squared over r equals mg tan theta. Johnny, can semi-trucks and motorcycles use this same on-ramp and off-ramp? Yeah, why? The mass can't really. Well, that's convenient. William, how I get the v by itself? Divide over the radius? And can you see we're going to get the square root of GR again with some other stuff, but we've seen that square root of GR appear before, which is kind of comforting. It suggests I'm pretty sure I'm on the right track. And so, yeah, this, by the way, is how they calculate the speed limit that they post when you're hitting an on-ramp or an off-ramp, okay? Or for racetracks, professional racers, they would actually know ahead of time what the sweet spot speed at whatever corner is. And we'll actually look at some actual racetracks later on in the homework. We get this. V equals GR tan theta square root. It's going to be the square root of 9.8. What was the radius? I've scrolled down. 55 meters. Tan, what was angle theta? What was theta? 23? Tan 23, square root of that. And I get 15.1 meters per second, or times by 3.6. 55 kilometers per hour. Okay. Suppose the road was covered in ice, no friction. What would happen if you went too slow? What would happen if you went too slow? You would slide this way. We'll write that in a second. What would happen if you went too fast? You would slide this way. Now, if there is friction, there is actually an extra force. If you're going too fast, friction is pushing you down, keeping you from sliding off. If you're going too slow, friction is keeping you up. So in real life, like on a sunny day, there's enough friction that there's a fair range of speeds that you can hit. But the reason we build banked corners is if you look at the speed limit and you hit it at that speed limit, even if it's rainy or crappy weather, you're completely safe. In fact, don't slow down. Not on a banked corner. That's when you could be in trouble. Is that okay? So, too slow. Slide down towards middle. Too fast. Slide up off of corner. Last one. So let's do a real problem. You're an engineer and you've been commissioned to design a racetrack for NASCAR. You're stuck in terms of the dimensions with a banked corner of radius 165 meters. You want the drivers to be able to take the corner at a pretty good speed, 45 meters per second. 45 times 3.6, 162 kilometers per hour. You want this to be a pretty exciting race. What angle theta do you need to design the track? Okay. So we have this same idea. There's our race car. What are the forces acting on it? Get the obvious one. Gravity. Good. And again, normal force. We don't want friction to be a part of this. So we get the same vector triangle. We get gravity down, normal force up. I know to stop drawing right there because that's what gives me a net force toward the center. There's angle theta, color, color, color. There's angle theta, color, color, color. Do I know the normal force? I don't care about the normal force. I'm going to use these two here. Again, which trig function is it? Okay. So I'm going to get tan theta equals opposite over adjacent. Tan theta equals mv squared over r over mg. Johnny. Johnny. Thank you. And I'm dividing by an r and a g. A better way to write that would be to write it as tan theta equals v squared over GR. What's this question asking me to find, Nina? How do I find an angle? Shift, it's either second function or inverse or shift, whatever it is on your calculator. Okay, this isn't going to be too bad then. So I'm going to get tan, wow, try writing that again, Mr. Dueck. I'll get tan of mystery angle theta equals, how fast do we want them to go? 45 squared. All over 9.8 times, what was the radius? 165 meters. 45 squared divided by bracket 9.8 times 165. Shift tan of that. Make sure you're in degrees. Some of you may find you're in radians, or you might be in radians soon in pre-calc. And I get 51.4 degrees. Okay. So the banked corner, a really neat application. It is a horizontal circle, although it doesn't look like one. But the car itself is tracing out a horizontal circle partway up the corner. What's your homework? Number 1. Number 2. Number 3. 4. 5. 6. So 7 is good. 8 is good. I think I'm assigning almost all of these. 9 is good. 10 is good. 11 is good. Yep, 12 is good. All of them. Ah! It's okay, we're in the home stretch here.